Then what I'm going to do is I'm going to start by giving a brief introduction to where things are at with yT. So the very first thing that I'm going to do, and again, not everybody has two screens, so this isn't necessarily going to be, you don't necessarily have to follow along, but I'm going to show you a little bit about how we get started with yT and how you might use it to access data and think about the data. So yT was originally created to deal with simulation data, specifically cosmological simulation data, but not everybody uses cosmological simulations. So there are lots of other, it's been applied to a bunch of other um, types of data as well. As you can tell, I'm sort of stumbling over my words and I'm feeling rather nervous today. So I hope you'll bear with me. My biggest fear is that I will say something uh, that isn't true. So please bear with me. It's a bit of a crazy time. Um, the very first thing that we do typically with yT is we import it, and yT is built on a number of different pieces of software, including um, NumPy, Matplotlib, Cython, SymPy, and a number of other pieces of software. And in fact, it exists kind of in this broad data ecosystem inside Python. So in fact, if you import yT, part of what it does is it imports Matplotlib, H5Py, and a couple other things as well. So yT has a number of different top-level modules, but the way that it thinks about data is it thinks about data as being registered as part of a data set. So typically a data set in yT is drawn from cosmological data or from any type of, from simulation data, has an associated parameter file, and then with that parameter file, some type of data that exists scattered about on disk. And so yT breaks this up into thinking about data as existing in bits that live on disk. On top of those bits, there's some sort of a data structure. And then out of that, what we want to do is we want to synthesize a model from our data. So my background was in the formation of the first stars in the galaxy, or the first stars in the universe. And so what I wanted to do with when I used yT to apply it to my simulations was I wanted to have it take a look at the data that was distributed about disk and then enable me to decide how I can interpret the stars and gas clouds and so on that that data represents. So the first thing that we're going to do when we load up yT is we want to load up a data set. So recently, and this is only in yT4 right now, but will be, that'll be in release very soon. We have a number of different sample data sets that are provided. And in fact, if we go to ytproject.org/data, you can see all of these different data sets. So up here at the top, you'll see there's some from the Arapo front end. We've got some from ArtIO, AMRVac, Athena, Athena++, BoxLib, the CF Radial, Chombo, Enzo, EnzoP, Exodus, Fitz, Flash, Gamer. They're in somewhat alphabetical order. And then down here at the bottom, yT data front end. Which we'll talk about a little bit later. We've also got a number of SPH data sets in various different formats, and I'm going to spend a fair bit of time, I think either tomorrow or the day after, talking about how yT thinks about discrete and SPH data. So I'm going to start by loading up a sample data set. And my favorite sample data set is Isolated Galaxy. Isolated Galaxy is a sort of low resolution galaxy data set that kind of looks like a galaxy. And so when we do ds equals yt.loads_sample isolated galaxy, what it first does, and this is a function of the load sample, is it figures out if it needs to download it, and if it does, it downloads and untars and so on. But then after that, yT goes out and it parses a bunch of information off of disk. And there are different stages to the parsing process. The very first thing that yT does is it tries to interpret all that it can about the data set without reading any of the actual data from disk. And specifically, that means that it goes and it reads the parameter file. In the case of Enzo or Gadget or Flash data, it reads all that it can without actually inspecting the structure of data on disk. So all of the different metadata that is accessible. And we can see that by looking at something, a dictionary called ds.parameters. Now for an Enzo data set, those of you that have used Enzo before, you'll know that the parameter file is something like 10 million lines long. That's an exaggeration, but not by much. And it has any number of pieces of information in it. So if I look at ds.parameters, it's going to bring back a dictionary. Oh, it seems I didn't get, oh, Medican, did I forget to rebuild?
Yeah, you didn't rebuild. This should
Okay.
be, if you, but it's a one-line change. It should be not an issue once you rebuild.
So if I look at ds.parameters, now you'll see that everything that it's able to tell about the data set is now included in there without actually having read any data off of disk. And so for an Enzo data set and for a Flash data set or for a particle data set, this is all of the metadata that is accessible without actually opening any HDF5 files or binary files and without reading any of the data off of disk. So this is for some data types, this is going to be very extensive, and for other data types, it can't infer all that much information about the data set. But it does provide us with a number of different pieces of information, like we can look at the domain width, we can look at the domain left edge, and we can look at things like domain dimensions. Now this means a lot for an adaptive mesh refinement or a unigrid data set where the data is in a finite volume, or but for Lagrangian data sets like particle data sets, this isn't necessarily as meaningful. In addition to this, it parses out information about the different units that are accessible. So if we look at ds.timeUnit, we can see that the time unit is 2.3296946 seconds. Now, this becomes relevant because we're able to do things like looking at the current time in the data set. Now, we'll talk about units a little bit more in a bit, but the reason that this is interesting to us is that we can do things like in units year. And so we can see this is 4.4 times 10 to the 8 years since the start of the simulation. We can also do things like ds.domain width, and we can look at that in any number of different units. So we can look at that in MPC, see it's just over 1. We could also look at that in furlongs. It has a number of different units in it. We could look at it in meters. I don't think we have any other fun ones. Maybe our sun. Yeah, we've got our sun. But we have all these different units that it self-consistently represents. Now, the first thing you might be asking if you're familiar with the Python in astronomy landscape is how does this differ from, say, AstroPy units? And I want to note that it's not actually different from AstroPy units except it's different from AstroPy units, but it is interoperable with AstroPy units. So if we were to do domain width .uq to AstroPy, we can actually convert it into, oh, it looks like I don't, yeah. Someone that has it installed would be able to get, but in my clean environment, it doesn't exist. It is interoperable with that, but the reason that we have a separate system here where we track the units differently is because we use symbols like code time and code length. Now, those of you that are simulators know that the units that are used internally in simulations are often scaled so that the values are as close to unity as possible. The that means then that when you're loading different simulations, oftentimes your units will be similarly scaled, and they'll both be code length or code time, but they'll in fact refer to very different things. So if I were to load up one of my simulations, I would also have code length running from 0 to 1, but it would refer to something completely different from what code length is in this system. And so we need to be able to manage that along with varying cosmologies to ensure that we have self-consistency inside our simulations. Okay. So the next thing that we do with the data set is oftentimes so once we've loaded a data set, we have essentially what amounts to an empty vessel here. So in this particular data set, the current redshift is equal to 0. But if we were to load a different data set, so I'm going to load sample Enzo cosmology, Enzo tiny cosmology. The redshift here is essentially 0 to round off error, but we end up with different domain width in megaparsecs, even though they correspond to the same code length. So the reason that we allow for loading up all of these different data sets without reading any data off of disk is so that you can apply some type of a selection at the top level. So for instance, if I have a number of different data sets and I'm only interested in ones where the redshift is less than 6 or something like that, I can load all of them up without expensively reading data off of disk. Now, the first time that I actually try to access any data, it will in fact read data off of disk. There are a number of different ways that we can access data, but all of them rely on what I used to call lazy loading and what I now like to think of as reluctant loading. So at this point, the only data that's been read off of disk has been the metadata for the simulation itself. But what we want to do next is we want to actually read some data into yT. So I hope that I'm not stepping on the toes of any of my fellow presenters by showing this, but we have a number of different selection representations. And what I'm going to do is I'm actually going to show a presentation that I've given in the past about how yT thinks about data. So we start out by, and can everybody see my pretty graphics here?
I see pink clouds.
Yeah, so I actually took this picture. What do you think, Stephanie?
I love it. It's beautiful.
Thank you. It was in the parking lot of a Meijer in Michigan. So when we see physical phenomena, so for instance, clouds or gas clouds in the universe or stars or anything like that, we have this assumption that we can model those in a way that reflects the underlying physics. So as an example, sometimes we see clouds that are like this. Now this is the type of thing that I'm sure people love in fluid dynamics. We've got some number of equations that apply, and we have this assumption in simulations that if we apply these equations in sequence or in some type of a controlled setting, we can evolve our data in order to match some type of observed phenomenon. I can tell that I'm getting really mush-mouthed already. I've only had 7 cups of coffee, so I'm a little bit low this morning.
That is the problem with
I
not
know.
having the coffee vat right next to us in the meeting room. Yeah.
Yes. So one way that this might look is you might have some type of a time series, some some type of simulation data. And over time, it evolves to look differently based on application of these equations. So what yT does is it constructs a vocabulary for analyzing this data. And that vocabulary essentially boils down to the notion of having a registration of data sets. So knowing where data is, knowing how data on disk applies to other data on disk, and knowing how to load pieces of data that correspond to some type of a spatially registered system. So in some cases, this might mean that the data is spread out throughout different HDF5 files, or throughout different raw binary files, or that the data is perhaps generated in memory from some type of a model. The next phase is where we can apply some type of a transformation to that data. So I'll explain in detail what I mean by that later, but essentially it means that we have fundamental quantities that may or may not actually exist on disk, and then we have a system of quantities that exists in potentia that don't actually have disk-based correspondence. We have selection, where we identify different regions that we are interested in, whether those regions are spatial or defined based on some type of a non-spatial quantity. And then finally, we have a reduction operation, where we take all of our different quantity, or all of our different transformed and selected data, and then we generate some type of a reductive analysis, where instead of having spatially organized and registered data, we're generating some type of a smaller set of values that describe it. So from the perspective of registration, that might be that the data is laid out on disk in some manner. Perhaps that data reflects the spatial organization. So maybe there's some sort of a load balancing operation that is applied, or maybe all of the data from this region is stuck in this file and all the data from this region is stuck in that file, or maybe it doesn't actually reflect that. What yT does is it generates a logical data structure that represents the data in memory so that you can access it with respect to its spatial organization. And then as a second step, what it does is it provides some type of a transformation to a data space coordinate. So instead of our logical in-memory organization, it corresponds to some type of a geometry. So the ultimate output of all of this is that we want to have some type of a function that can query specific data fields at every vector location. So having a functional representation of the data, so an f of x, where x is some vector quantity that's here or here or here, having some mechanism of defining how to compute that. Now with finite volume methods, that's reasonably straightforward in the sense that we have this logical representation that can be that it fills up all of the different regions, it tessellates the domain. But with other types of representations, for instance, particles, or any type of discretely sampled data, you can register this on disk so that instead of applying a function that is exclusively local, you have a function that, for instance, applies a smoothing kernel across these points in order to define the value at any given point in the data set. So the next phase of what yT thinks about is it thinks about transformations of data. So the way that we think about transformations of data is that you have some set of primitive variables on disk, and that these can be combined in many different ways to produce fields that exist in potentia. So for instance, in our isolated galaxy simulation, we store the density, the velocity, the internal energy, and so on. But we also store things like the velocity in the x direction and the velocity in the y direction. What we can do with these types of quantities is we can combine them to generate a quantity that has physical meaning. So for instance, the velocity magnitude. But we do that on demand only as necessary. So we have what are called derived fields in yT. There's the set of fields that exist on disk that yT knows how to read, knows how to convert into some type of a semantically meaningful set of units. And then we have the set of derived fields. And those derived fields don't exist until they are requested. So for instance, we have the y velocity, the x velocity, and these can be combined to form the velocity magnitude, which doesn't exist until it's requested. The next phase of what yT thinks about is we can also generate selections of data. Points can be points which include cells or other types of values can be generated based on, can be filtered based on connectivity, on their organization, or even from criteria from one or more of their field values. So as an example, let's go back to our Kelvin-Helmholtz instability. We might have some type of a histogram of, value. This is the level of the cells that are selected. We can select based on, say, a rectangular region. And then as we move our selection around, our histogram can update and we can see where things are and how many cells of each type are selected at any given time. This can also be applied in ways that aren't related to spatial selection. So for instance, it could be based only on the density criteria. So for instance, I'm only interested in density above a given threshold value. But it also doesn't have to just be this rectangular set of selections. It can also be anything that could be defined geometrically. yT has built-in selections for spheres, or again, rectangular prisms, disks, ellipses, and then Boolean combinations of any of these items. Now, where things get really fun, where we've been working a lot lately, are in reductions along axes and paths and even non-trivial manifolds. So one way to think about this is you can construct, say, a path, and then you can conduct queries along a given path. That path could either be constructed manually, which is what I've done in this particular instance, or it could be constructed from some set of integration points. So integrating along a velocity field or something like that. You can query along those and then gain and then access the values at each point and then conduct integrations along them. We also have projection operators. So projections are where you integrate along an axis. So for instance, integrating the density values along the x-axis, or where you either conduct a path integration, where you conduct some sort of a reduction operator like min or max, and other operations like that. Now, finally, all of these operations can be composed. So for instance, we can take a full set of data, register that data, and then, wow, that's super irritating. There we go. Yeah, the bouncing wasn't supposed to happen. That's no fun. Where you register all of your data, and then on top of this, you apply some set of selection criteria. So for instance, you might identify and find all of the different dark matter halos, and then each dark matter halo you apply a reduction operation onto in order to compute, say, its virial mass or radius or something like that. And then you register it into a new system of organization. So let me get back to where we are with yT. And so now, if we look at our original DS, this is our isolated galaxy. We can see some of these things in place. So we can look at field list. And what it just did was it went out and it read data from disk in order to identify which fields are accessible. These are all the different fields that it knows about on disk. So when yT reads data from disk, it constructs a field tuple. So the first item in this, when it thinks about fields, is the field type, and the second is the field name. So here, our first item, Enzo and BX. What this is a primitive field as it is stored on disk. But YT also constructs a number of aliases. So it knows about things like density and temperature and velocity, and it creates pass-through fields. What this enables is it enables the same analysis script to be run on data sets from many different types of data. So for instance, you can run the same analysis script on an ENSO dataset as you would on a Flash dataset by using the same names for all of your different fields. I'm going to look now at the derived field list, but I want to note this is a really long list. So here, these are all the different fields that it knows how to generate. You'll see here that the on-disk fields are mostly all the same, but then we have gas fields. So when you're dealing with simulations that include gas dynamics, YT constructs a number of different aliases for gas fields. So you'll see that here under gas, we have things like density gradient in X, density gradient in Y. We also have the path element in X, which comes in handy for non-Cartesian geometry. And then we also have vertex X, velocity Y, and velocity Z. I'm going to clear the output from this cell because it's enormous. And I'm going to show you what's called the fields list. So if you do ds.fields.gas, let's take a look at velocity X. So ds.fields.gas.velocity_x is an alias field. Velocity X aliases ENSO X velocity, and it's in the units of centimeters per second. Now, if we look at ds.fields.enso, and actually that's not tokenizable, so ds.fields field info ENSO X velocity. This is an on-disk field with units of code velocity. All of these different gas fields, when they're aliases, simply alias and fix the units. So if we look at ds.fields.enso.D density, and then we compare that to ds.fields.gas.density, gas density is an alias field that converts into the correct units and is consistent across all the different front ends. So when I load up a Flash dataset or a Ramses dataset or a Gadget dataset, these are consistently defined.
Matt, it looks like we have a question from Madikin.
Oh, hi, Madikin.
Hi, Matt. Can you explain when you did the field list, the difference between IO, ENSO, and N-body fields?
That's a very good question. So, and that wasn't a plant either. The way that that the particle systems work in YT is that by default, if you only have one type of particle, it's an IO type particle. We also set up particle unions. So if you have multiple types of particles, you'll get a particle union that is all, and you'll get a particle union that is type N-body. So this is mostly useful for front ends like Gadget, where you have some particles that are N-body, some particles that are gas, and sometimes you want to access all of them. So in that case, you would have all fields for all of the particle fields that exist in all types of particles. And actually, I will go ahead and demonstrate this. So if I do load sample, and I load up a Gadget data set. Oops. So you'll see that for a gadget data set, and this is actually from an OWL simulation, you get things like particle type 0. It has all these different fields included. Particle type 1 has only coordinates, mass, IDs. Particle type 4 has all of these. And so then this particle union for all is set up, and it only includes the fields that exist for all of the different particle types. And then n-body is set up, and it only includes all of the particle fields that exist for the n-body types, which in this case are just particle type 1. I think tomorrow I'm going to show particle unions and particle filters in more detail.
Okay, so I have a quick question then. So then tomorrow is when
Or
you'll.
is it the day after?
No, tomorrow. Okay. So tomorrow is when you'll answer, like, if I just typed in coordinates, what would YT assume between like all gas and n-body?
I mean, I could do it right now.
Okay, I mean, whatever you want. It can either be tomorrow or now. I don't care, as long as it gets answered sometime for me.
Okay. So if you specify the particle type, it will just give you the coordinates for that particle type. If you specify all, it's a concatenation of all of them. So we can show this if we do something like dd equals ds.r for all, and I'm using stuff here that I recognize I haven't demonstrated yet.
Oh.
But now if I just do n-body, you'll see that it's way less.
Right, but sometimes I'm lazy, I think, and what I do is I just type coordinates.
Yeah, so that's a really good question. That what it tries to do is so as of right now, YT will try to figure out what the most recent one that you asked for was. So if I do this now, dd coordinates, it will do it as though I had just done part type 0.
Okay.
But that's ambiguous, right?
Mm-hmm.
And we're actually going to make it raise an error very soon.
Okay, cool.
See, because this is not good right there. Okay. So it's ambiguous, and so right now it tries to do the right thing, which is not often exactly what you want. So it will be raising an error in case of ambiguity in the near future.
Cool, thanks.
Okay. Let's see, it is, okay, let's see, what do I have next? So let's talk a little bit about derived fields again. One of the things that is most important with derived fields is knowing exactly what you're getting. So if I were to do gas and then I were to do, let's say, velocity magnitude, you can see that's a derived field. But I can also see a number of different properties about that derived field. One of the most important ones is what the source code was. So I can do ds.fields.gas velocity magnitude, and unfortunately I have to print it. And it shows to me exactly the source code for that derived field. In this case, it's not terribly informative, simply because it is run inside of a field plugin, but it's there. So unless there are any objections, would it be okay if I move on to a little bit about inspecting data structures?
I think we're good. I don't see any hands.
Okay. So the main way that we create data that we access data in YT is through data selectors. So the very simplest data selector is one that we've already seen, which is the all data selector. All of our data selectors hang off of the dataset object. So remember our DS here is Galaxy 30. And we can do dd equals ds dot all underscore data, and we call that. And what that creates is it creates a YT region. It's centered here at the very center. It's got a left edge that's at the left edge, and it's got a right edge that's at the right edge of our simulation. And we can now access data that exists inside it, just like by accessing a dictionary. So if I access DD density, YT goes out, it reads all of the data off of disk, it converts that into our lowercase density, and then it returns it to us as an array. So this is how many cells there are. And now the thing about using this with AMR data, with adaptive mesh refinement data, is that oftentimes you'll have data that's overlapping, or in fact, that's kind of the thing with AMR. You'll have data that's overlapping, and YT only returns to you the data that is at the most fine regions inside your data selector. So for instance, any refined regions, the non-leaf node values are not returned to you. So we can do fun things with this. We can divide it by 2, it's a NumPy array, basically. We can do any number of different things to it, and we can also convert it to different units. So let's do in units. Let's say kilogram per MPC cubed, and it converts it. Unit conversions are super fun. But it also is keeping that data resident in memory. So when we do this, until we access a data field, it doesn't exist. But once we access it once we access it in this way, where we access our data selector like an array or like a dictionary, that data is now stored in memory. Now, for very small data sets, like our isolated galaxy, this isn't really such a big deal. However, for much larger data sets, this becomes very cumbersome, especially because having all that data resident in memory means that it's resident in memory. So we also provide access to aggregators like min. And what these aggregators do, like min, max, mean, sum, and so on, is they do this reluctant loading process, where YT has an understanding of the index system that is used in the data set. And it uses that understanding of the index system to only read as much as is necessary at any given time. So YT has a chunking system that operates under the hood. It utilizes that chunking system in order to construct data parallel operations. This happens also with things like max of density, mean of density, and we can weight this by things like cell volume. And so these different operations, rather than reading any of the data off disk and retaining it in memory, read only what is necessary and then apply accumulators to the data. So if we were to sum up the cell volume, you'll see it gives us our centimeters cubed. And we can also now do domain width dot prod. And let's see what that looks like. Exactly 1, so that's good. The sum of the cell volumes is exactly equal to the size of the domain. Now, I'm not going to step too much on other people's stuff, so I'm not going to show you some of the really cool stuff that you can do with mean. Like you can do mean of density along a given axis, and you can say that axis is X, for instance. That would be conducting a projection. We're not going to do that. But you can do things like argmin. So let's say that I want the temperature, the velocity magnitude, and the density at our minimum density point. Sorry, I had that completely backwards.
And when you have a chance, Matt, we have a question from Sabrina.
Okay. Let me finish. Yes.
Great.
So we can do things like give me the argmin of density, and that'll tell me the position of the minimum density. We can do argmax of density, and that'll give us the maximum value. And then we can also say what the axes are that we're interested in. So in this particular case, I said I want the minimum density location, but I want you to tell me the values of temperature, velocity, magnitude, and density at that location. So you'll see that here, yeah, so the argmax, oh, it's slightly different. Well, that seems wrong. What are the axis of temperature, velocity, magnitude, and density? Anyway, yes, Sabrina, is it a text question or do you want to speak?
I can speak.
Okay. Hi,
And
Sabrina.
you may have said this and I just missed it, but earlier you were having to include that sort of first entry on the field in order to make sure you're getting the appropriate density, and now you're not.
Mm-hmm.
Why is the change?
So that's a very, very good question. So there's no ambiguity here because it's a single fluid simulation. And so all of our density values are gas density.
Okay, so it's the nature of the specific simulation, not because you've
Yeah.
looked at a specific region.
That's right.
Okay, thank you.
Ask a question too.
Mm-hmm.
Two questions actually. So first off, you did a all data to get to your, but previously you did a ds.r.
Yeah.
It is equivalent, or
They are.
okay.
And I shouldn't have done ds.r just because I have I think Madikan, are you covering ds.r? Is someone else covering ds.r? If not, I'll go through it.
I was just going to mention that it's a region selector. So
Okay.
But I mean, you can go into it. It's okay.
Okay. Yeah, then I think I will. So ds.r. So I'll show one other selector first. So another common one is sphere. So usually I just call these spheres or SP. Sphere takes a center argument and a radius argument. So SP equals ds.sphere. And our center, we can either specify in code units as like 0.5, 0.5, 0.5, or we could specify C for center, or we could even specify max for the maximum density location. And then our second argument, our radius, we can specify either using field locations or either specifying values, or we can specify it using what's called a unit tuple. So if I wanted it to be 1 megaparsec, I would specify 1.0 comma megaparsec. So it goes and it finds the maximum value. Oh, sorry, it's already done. And now we can access that. So here we can do something like the sum of cell volume, and it gives it to us here again in that. So let's do in units, code length. Oh, because our simulation is much smaller than that. Let's do 1 kiloparsec. Yeah. There we go. So ds.r is a ds.r is a quick way of specifying regions that can be defined in terms of rectangular prisms. So it accepts slice notation. And if you just want the entire data set, you can just do ds.r and then a slice, colon. That's functionally equivalent to ds.all-data. But you can also specify a left edge and a right edge along each dimension. And so if I specify this, it gives it to me from 0.1 to 0.9 along x, 0.1 to 0.9 along y, and then 0.1 to 0.9 along z. And so if I were to do, region is equal to that, and then I did region.sum cell volume in units, code length cubed, see that it's much smaller. Now, one thing I want to note is that the way that yT does cell selection is that it selects based on the cell centers. So it's not going to exactly reflect, it's not going to be exactly 0.8 cubed. It's going to be a little bit higher because it has a tendency to over-select as a result of selecting based on cell centers. Now, there are other things you can do with R. So for instance, I could slice along the x-axis everywhere along the y-axis, and then do 0.5 along the z-axis. And actually, let me not assign that to region. And this gives me a yT slice. So it slices along axis 2 at some given coordinate. And then if we were to do an exact point, it actually gives us back a yT point selector. You can do a bunch of fun things with this, like you can request that it regularize the entire domain. And so there it gives us a grid that's got dimensions of 128 cubed. But that all will come in a little bit later. So the last thing that I want to show before before we take off is I want to show an example of how you might do a derived field. So oftentimes you'll need to specify your own derived fields. yT has a whole bunch of them available, but oftentimes you'll want to create your own derived field. So what we specify with derived fields is we specify a function that generates them. And so I always use dinosaurs as my example. And our function takes the field definition and it takes a data object. So I don't know how many of you out there are actual dinosaur experts. I believe those are called paleontologists. If you are, please go ahead and raise your hand if you want to correct me on this. But it turns out that dinosaurs scale like temperature cubed divided by density squared. So what we do here is we return our data, temperature cubed divided by data density squared. Okay. And we can now add a field to YT. And this field we'll call dinosaurs. And we'll specify our function is dinosaurs. And then it should compute the units. And so now we've got DD, and we can access the dinosaurs field. Looks like we need to specify our units. So one thing that I always run into forgetting how to force, yeah, I said force override. I guess let's just do auto. We'll call this dinosaurs 2. And so we get our derived field units right here. Now, normally you'll know what units you want it to be in, and you won't have the same trouble that I did, but you can also debug it doing the same thing that I did, where I did it a little bit ad hoc.
I think you might have a question from Ari, Matt.
Hi,
Is
Ari.
that- Did I totally make that up, Ari?
No,
okay.
but Matt's gone on so much, I've gotten distracted.
Oh,
by
I'm
what he's talking
sorry.
about, so it's
Sorry
fine.
about that.
I think we can continue where we are.
Okay, sorry about that.
Yeah, we had an email between the organizers of the conference the other day about hand watching, and I had a pretty funny joke that I wrote back that I'm going to share with everyone here. And that joke was that we should all make sure that we hand watch for long enough that it takes to sing the ABCs. I will take the lack of laughter
Ching.
to be muted microphones. Okay, so I think at this point I need to take a break. Is it okay if we do a short if we accelerate our break to now?
Sure, of course it's fine.
Okay, and it would be okay with me, but maybe not with our next presenter if we started 20 minutes early, because we're ending mine 20 minutes early.
I would say let's start as the schedule says, because I think
Okay.
people may come in and out.
Yeah.
Okay. So
Can I ask a quick question before we?
Oh yeah, please
take break?
ask a long question if you want.
Long question. 20-minute question. Just to try to get clarification, the data call that you do inside the derived field function definition, is that structurally the same as basically when you've done an all data call to create the this variable that was DD before?
So that's a really, really good question. The answer is no.
Okay.
So internally, what YT does is it does what's called a chunking call, and so this will all be bonus content. So what it does is it does for chunk in dd.chunks, and then it usually specifies if it chunks based on IO or whatever, and then it generates a field here. And so with data sets where you've got particles that are spread out between different files on disk, each IO chunk is going to be some subset of the particles in each file, or if it's grids, each IO chunk is some set of files or subsets of grids. So it will generally look like a flat array, but this function will be called multiple times and then concatenated at the end. And so this allows it to do things like if you're just generating the mean value, what it does is it just runs the accumulator, and it reads just what is necessary for the intermediate step in the accumulator, and then it discards that at the end. Does that make sense?
Yes, but syntax-wise, if I was
yes.
trying to debug a
sorry.
call, it would be a very
Yes.
similar use.
Yes, syntax-wise, it's identical.
Okay.
You can make it, you can request things like, you can request that it comes to you in some three-dimensional form, for instance, but in general, it'll be a flat one-dimensional array.
Thanks, Matt.
Mm-hmm.
Okay, we've got another question from Mike.
Hi, Matt.
Hi, Mike.
I've got a question. I might have asked you this in the past. You said when you do these reductions that it only uses the leaf nodes.
Yep.
Just to make sure, it's not assuming that each patch has only one parent.
It does not assume that each patch has only one parent. That is correct.
Okay.
So that's usually set by the front end.
Yeah, it's it's a weird tree
Mm-hmm.
in that sense.
Yeah. So
Branches merge.
yT has support for multiple parents and
Okay.
overlapping at the same level as well.
Okay, cool.
So a lot of these a lot of these actually arise from the same lineage of code that you use typically.
That's right. Yeah. The original Burger and Colella had multiple parents.
Yeah.
Cool.
Okay, do we have any other questions before we take a nice long break? Let's give it maybe a minute here to see if anybody's thought of anything. You can put down your hand, Mike, if you want. I don't have host, so I can't force it. Unless you had another question and I was just shutting you down, in which case.
No, I forgot how to put it down.
Okay, good. All right.
So I haven't shown any visualizations yet. Maybe I should just do one real quick, just because.
I'm gonna do one.
Okay, sorry, you're right. I don't want to.
Yeah. Okay. Well, I say so. I think all of the organizers are in agreement. We're going to get back rolling at 11:30 with our next one, which puts us right on the schedule. Which I'm going to post a link to the schedule on the Slack channel in case anybody is having trouble finding it. And yeah, great. 11:30. And before we go on at 11:30, we're going to try to go around and do names, which is, as far as I can tell, it's like one of those get to know you exercises where you're supposed to just like look around and know when you say your name, except you're not actually in the same place. So it's a nearly impossible exercise, but that'll be fun. And then we'll get rolling with the next session. And thanks everybody for signing on.
And one more thing, Stephanie, I believe it's the case that at some point Matt will put this notebook up online.
Yes, I should have it up in very soon.
Cool, great. And I had one more thing. Oh, right. I don't think that this Zoom line isn't going down. So you're welcome to just, like stay here and stare at the screen or whatever. And then just come back to your computer or, start paying attention again at 11:30. I hear there's something happening. Should we? Oh, okay. Yeah. Matt, I think we have you. Do you want to do this Tails thing now or later?
No,
I'm confused,
I
I'm
broke
sorry.
whole tail, it turns out.
Oh, okay, good. Then
Yeah,
let's not do that now then.
Yeah, I as I always tend to do.
That's breaking things is good. That makes them
Yeah.
stronger.
Good.
Good.
I'm going to stay on as well. So we can, yeah, I'll be around for questions and discussions.
Perfect. Okay, and then at 11:30, Madikin's going to go, and we'll keep on trucking. Thanks, everyone.